Have you ever wondered what the future of computing might look like? Can light play a significant role in it? If such questions pique your curiosity, then you're in for a treat. A team from the University of Cambridge and Microsoft have made a breakthrough in the field of computing, introducing an optical computer capable of solving optimization problems at nearly the speed of light. Yes, you heard that right, the speed of light. Now you might be wondering, what exactly is an optical computer? Well, it's a type of computer that operates differently from the conventional electronic computers we use every day. Instead of using electricity, these computers, also known as photonic processors or light-based processors, use light. That's an exciting shift, isn't it? Over the past few years, researchers have been developing various versions of these light-based processors. Each of these processors has different architectures and levels of functionality, but they all share a common goal: solving combinatorial optimization problems. These problems, while of great practical interest, are computationally intensive even for the most powerful electronic computers. But what makes the work of the Cambridge and Microsoft teams stand out is their new architecture, known as the Analog Iterative Machine, or AIM. This architecture takes a unique approach to solving these complex optimization problems, leveraging the properties of light to perform calculations at an unprecedented speed. These computers, known as photonic processors, could potentially solve optimization problems at nearly the speed of light. And that, my friends, is the bright future of computing we are heading towards. To understand why this development is groundbreaking, we need to delve into optimization problems. These are mathematical challenges that necessitate finding the optimal solution from a set of viable alternatives. To put it simply, it's like trying to find the shortest route for a road trip that covers numerous cities, or determining the best mix of investments for a financial portfolio. Now, these may sound like everyday problems, but when the variables increase, so does the complexity. For instance, managing electricity and power grids, streamlining goods deliveries, optimizing internet traffic routing, and composing asset portfolios in financial markets all rely on efficient solutions to these optimization problems. A small-scale optimization problem could be solved by a conventional computer in a reasonable amount of time. But with larger instances, things get a bit trickier. Imagine a supercomputer, the world's most powerful computer, being occupied for years or even centuries trying to find the ideal solution. That's how complex these problems can be. The challenge lies not only in the sheer number of possible solutions, but also in the difficulty of translating real-world optimization problems into binary representations. This is because all existing approaches require optimization problems to be translated into this binary form. And let's not forget that this translation process is extremely challenging. Consequently, the need for a more efficient solution has led researchers to explore various hardware and architectures. These include traditional field-programmable gate arrays, quantum annealers, and electrical and optical parametric oscillator systems. And among these, optical computers, using light rather than electricity, have emerged as a potential game-changer in solving optimization problems. The Cambridge and Microsoft team's innovation is a new architecture called the Analog Iterative Machine, or AIM. This machine operates differently from the conventional electronic computers that we're used to. It's an optical computer, sometimes referred to as a photonic processor, that uses light rather than electricity to solve problems. You might be wondering, how does this work? Well, it all comes down to how photons interact with matter. While photons typically do not interact with each other, they do interact with the matter through which they propagate. This allows for linear operations like addition and multiplication to take place, forming the basis for optimization applications. For instance, when light falls on a smartphone's camera sensor, it sums the received photons and generates an equivalent amount of current to represent the collected color in each pixel. Furthermore, data transmission through optical fibers relies on encoding light in terms of zeros and ones by controlling its intensity. This scaling of light through light-matter interaction performs multiplication in the optical domain. But it's not just about linear operations. The AIM also makes use of various electronic components present in everyday technologies to perform nonlinear operations, which are critical to efficient optimization algorithms. And here's the real kicker. The team built their analog iterative machine using off-the-shelf components. That's right. The light sources include micro-LEDs that are already present in TV screens, and the sensor reading the response is the same CCD found in digital cameras. By using off-the-shelf components, the team has created a practical and efficient solution to real-world optimization problems. This isn't just a theoretical exercise or a proof of concept tucked away in a research lab. It's a real working machine that has the potential to solve some of the most complex problems we face today at nearly the speed of light. So what does this mean for the future of computing and practical applications? Optical computers like the analog iterative machine open up a whole new world of possibilities across various sectors. Let's take a moment to envision this new landscape. Consider our power grids. They're complex systems that require constant adjustments to balance supply and demand. By using light-based processors, we could potentially analyze and optimize these adjustments in near real time. This could lead to more efficient energy use and even contribute to efforts against climate change. Now, think about goods deliveries. Today's delivery networks are intricate webs that span the globe. Optimizing these networks is a colossal task, one that could take conventional computers years to solve. But with optical computers, we could streamline these networks more efficiently, getting packages to doorsteps faster and reducing carbon emissions in the process. And what about internet traffic routing? In our increasingly digital world, ensuring smooth and fast internet traffic is paramount. Optical computers could analyze and optimize traffic routes with incredible speed, improving our online experiences and even enabling new applications in areas like virtual reality and cloud computing. Finally, let's talk about financial markets. These markets involve vast amounts of data and require rapid processing for trading decisions. With the speed of light-based processors, financial institutions could make these decisions in the blink of an eye, potentially turning the tide of the markets in their favor. In each of these sectors, the common thread is the need for speed and efficiency, and that's precisely what optical computers promise. By operating at nearly the speed of light, these machines could revolutionize how we solve some of our most pressing challenges. As technology continues to evolve, we can expect to see more developments in the field of optical computing. So, can light play a significant role in the future of computing? The answer seems to be a resounding yes. As we've seen, optical computers, like the analog iterative machine, leverage the properties of light to tackle complex optimization problems at near light speeds. This is a dramatic shift from conventional electronic computers and could revolutionize the way we solve complex problems. The potential applications of these light-based processors are vast and far-reaching. They could improve how we manage electricity and power grids, streamline goods delivery, optimize internet traffic routing, and even compose asset portfolios in financial markets. The power of light in computing could quite literally brighten our future, bringing about a new era of speed and efficiency in technology. Furthermore, the development of the AIM by the University of Cambridge and Microsoft is a testament to the practicality of optical computers. By using off-the-shelf components, they've shown that an optical computing future is not just a theoretical concept, but a tangible reality within our grasp. However, like all burgeoning technologies, there are challenges to be faced. The transition from binary to analog computing is not straightforward, and the interaction of light with matter, although promising, is still a field ripe for exploration and development. But these challenges only serve to fuel the drive and innovation in the tech world. As we continue to push the boundaries of technology, the role of light in computing might become more prominent, leading us into a new era of speed and efficiency. The future of computing is bright, and it's powered by light.